All right, let's just jump right in. We're about to tackle one of the biggest, most important unsolved problems in all of computer science, and in mathematics for that matter. This is a question so huge, so profound, that there's literally a $1 million prize waiting for whoever solves it. We're talking about the mystery of P versus NP. So, what's this all about? Well, it really boils down to this one simple sounding question. Think about it like this. Say someone hands you a finished Sudoku puzzle. You could check if their solution is correct pretty fast, right? A minute, maybe two. But how long did it take them to actually solve it from a blank grid? That gap, the difference between easily checking an answer and the struggle of finding it, that's the heart of what we're exploring today. And, this question has gotten so famous that it's even popped up in the most unlikely places. Believe it or not, back in a 1995 Halloween episode of The Simpsons, Homer is walking through this 3D world, and for just a second, an equation flashes on screen behind him, and it says P equals NP. It's a total nerd joke, but it just goes to show you how big this puzzle really is. Okay, to really wrap our heads around this, let's start with a classic problem. It seems super simple on the surface, but its hidden complexity, man, it gets right to the core of what we're talking about. Let's talk about the traveling salesperson. The idea is simple. You've got a bunch of cities, and you need to find the absolute shortest route that visits every single one, just once, and then gets you back to where you started. With 4 or 5 cities, you could probably figure this out on a napkin, no problem. But here's the kicker. As you add more cities, the difficulty doesn't just grow. It explodes. The number of possible routes just skyrockets. If you have just a few dozen cities, the number of paths you'd have to check it's astronomical. A supercomputer trying to brute force the perfect solution for hundreds of cities would still be running long, long after our sun has burned out. So this is where we have to get a little more specific. We need to define what computer scientists actually mean when they say a problem is easy or hard. It really all comes down to how the solving time scales up as the problem gets bigger. First up, you've got the class P. The P here stands for polynomial time. These are what we call the easy problems. A good way to think about it is like finding the tallest person in a line. If you double the number of people, the time it takes you to find the tallest person pretty much just doubles too. The work grows in a predictable, manageable way. These are the problems we can actually solve efficiently. Now we have the class NP. That stands for non-deterministic polynomial time. Now don't get hung up on the non-deterministic part for now. It's a bit confusing. Just think of NP as the set of problems where the answers are easy to check. If I gave you a potential route for that traveling salesperson, you could quickly add up the distances and verify if it's correct. You can check the answer quickly in polynomial time, even if finding that answer in the first place seems impossibly hard. And this visualizes that difference perfectly. The blue line, that's polynomial growth. It curves up, sure, but it's manageable. Now look at that red line. That's exponential growth. It's not a curve, it's a sheer cliff. For computer scientists, this is the wall between what's solvable and what is, for all practical purposes, impossible. So the whole thing really hinges on this distinction. P problems are fast to solve. Finding the biggest number in a list, that's in P. NP problems are fast to verify. Our traveling salesperson problem is in NP because checking a route somebody gives you is fast. Factoring a huge number into primes is thought to be hard, but multiplying 2 primes together to check if they make that number, that's super, super easy. And this right here brings us back to the million-dollar question. Just because you can check a solution quickly, does that mean there has to be some clever, fast way to find it in the first place? Are these two classes of problems, P and NP, actually the exact same thing? But wait, the story gets even deeper. It turns out, to answer this massive P versus NP question, we don't have to study all the NP problems out there. There's this special, elite group that actually holds the key to the entire puzzle. These are called the NP complete problems. They're the heavyweights, the absolute hardest nuts to crack in the entire NP class. And what makes them so special is that they're all, in a weird way, the same problem, just wearing different disguises. If you find a fast, efficient solution for just one of them, you've basically cracked the code for all of them. And this is a fantastic way to think about it. An NP-complete problem is like a master key. It's a key that can unlock not just one door, but every single door in the entire NP building. That traveling salesperson problem we talked about? Yep, that's an NP-complete problem. And just look at this list. This isn't just some abstract math stuff. NP-complete problems are hiding everywhere. They're in biology when you're trying to figure out how proteins fold. They're in logistics, in circuit design, and yeah, they're even in your morning Sudoku puzzle. It's crazy how widespread they are. So how is that even possible? Well, it's through this powerful mathematical trick called reduction. Think of it like a universal translator. Scientists have figured out how to take almost any problem in NP and translate it into the language of an NP-complete problem, like one called the Boolean satisfiability problem, or SAT for short. So if you find a fast way to solve SAT, that means you can solve any problem in NP. It's a true one-size-fits-all solution. Okay, so let's play a game of what if. What would actually happen if someone proved that P does equal NP? What would that world even look like? Because honestly, the consequences would be nothing short of revolutionary. If P equals NP, our world changes overnight. I mean it. We could solve impossible logistics problems, design brand new medicines by perfectly modeling proteins, create truly intelligent AI. But there's a huge dark side. All of the digital security our entire world runs on would basically crumble. Instantly. Bank accounts, government secrets, all of it. Wide open. Now, if P does not equal NP, then our world pretty much stays the same. Encryption is secure, some problems are just fundamentally hard, and we still need that spark of human creativity to find clever, good enough solutions. For decades, the greatest minds in math and computer science have been trying to solve this. So, where do we actually stand today in the search for an answer? Well, for one, the Clay Mathematics Institute has a $1 million prize waiting for a formal proof. And this isn't just for bragging rights. It's one of their 7 Millennium prize problems, which tells you just how important this is to the world of science. So after all this time, after decades of trying, no one has ever found an efficient algorithm for any NP-complete problem. Not a single one. Because of that, the overwhelming consensus in the field is that P does not equal NP. But a strong feeling, even from the smartest people on the planet, is not a proof. And that definitive proof is still out there, somewhere. But here's the thing. Even without a final answer, the theory of NP completeness is incredibly useful right now. As MIT's Michael Sipser puts it, it gives us a roadmap. It tells us when to stop wasting our time searching for a perfect, elegant solution that might not even exist, and to start looking for clever approximations that are good enough for the real world. And that is incredibly valuable information. And all of this leaves us with one last, kind of mind-bending thought. The P versus NP question isn't just about computers and algorithms. It's about the very nature of creativity itself. Is finding a brilliant new idea, is that fundamentally harder than just recognizing a brilliant idea when you see one? Is that creative spark, composing a symphony, proving a new theorem? Is that just a really complex calculation we haven't found the shortcut for yet? Or is it something more, something that will always be fundamentally hard?